In this lecture video, we're going to be reviewing hypothesis testing procedures for a single population mean. Now there are two scenarios that we're going to be looking at. The first is testing hypotheses about a single population mean when the population standard deviation is known. That's called a z-test. We'll also look at testing hypotheses about a single population mean when the population standard deviation is unknown. And you'll recall that that is called a t-test. In this particular lecture video, we're going to be reviewing the details of the z-test. And in a subsequent lecture video, we'll take a look at the t-test. So let's take a look at the details of testing hypotheses about a population mean when the population standard deviation is known. Here's an outline of what we'll be looking at in this video. We'll first describe the sampling framework from which we get the data and which we'll use to test hypotheses about the population mean. We will list the three types of hypotheses that we can test about a population mean. We'll give the formula for the test statistic that we'll use in performing the hypothesis tests. Then, to each of the three types of hypotheses, we will describe and define the rejection region. Also, we will give a definition of p-values, and then to each of the three types of hypotheses, we will give the formula for computing the p-value. And then finally, we will give a couple of examples that demonstrate the procedures for testing hypotheses about a population mean when the population standard deviation is known. So let's jump in. Whenever we look at a new scenario, we're going to be discussing the sampling framework that we're operating in. It's very important to understand how a population is being sampled. There are many ways to sample populations, and the way that you sample a population will determine the appropriate method of analysis. So in this situation, we're going to let x1, x2, and so forth up to x sub n be a random sample of size n from a normal distribution, the mean of which is mu, and the variance of which is sigma squared. We'll let x bar, s squared, and s denote the mean, variance, and standard deviation, respectively, of the sample. Now, recall that the standardized random variable that we called z previously, which is the standardized version of x bar, and what that means is that we are subtracting from x bar the mean of its sampling distribution and dividing that difference by its standard error. You'll recall that that standardized version of x bar has a standard normal distribution. Now, where is this coming from? Well, remember that when we're sampling from a normal distribution, the sample mean is also normally distributed. The mean of its sampling distribution is the mean of the underlying population, which in this case is mu, and the standard error of its distribution is equal to the standard deviation of the population being sampled divided by the square root of the sample size. So in this expression here, we are subtracting from x bar the mean of its sampling distribution, which is mu, and we're dividing that difference by its standard error, which is sigma over the square root of the sample size. And so when we standardize x bar in this way, again, the standardized version of x bar, which we'll denote by z, has a standard normal distribution. Now this fact is used as the basis for hypothesis tests and confidence intervals for mu when sigma is known. If sigma is not known, then we're going to have to estimate it from the data. Okay, once we do that, then the estimate of sigma can be plugged into the formula above, but this will require using a sampling distribution other than the standard normal distribution. So here's the point that we're making here. In order to compute this standardized version of z, for example in the context of hypothesis testing, we need to know what sigma is. If we don't know what sigma is, then we can't calculate this expression. And so what we would need to do is estimate sigma using, for example, the sample standard deviation. But if we do that, then this expression, this random variable, with sigma hat substituted in for sigma, would no longer have a standard normal distribution. But for now, we're going to just assume for the moment that sigma is known. So that's the sampling framework that we're working with. We're sampling from a normal distribution. We're assuming that sigma is known, and we'll generalize that a little bit later. In testing hypotheses about a population mean, there are three types of hypotheses that we can test. A two-tailed test, where the null hypothesis says that the mean of the population is equal to some specified value, which I'm going to denote generically by mu naught. But in a real problem, in an applied problem, we would have an actual value here. The alternative hypothesis, which is the logical complement, the opposite of the null, would therefore be that the mean mu is not equal to that hypothesized value. Then we have what's called a left-tailed test. In the left-tailed test, the null hypothesis says that the mean of the population mu is greater than or equal to this specified value mu naught, versus the alternative hypothesis, which says that mu is strictly less than mu naught. And then finally have a right-tailed test, where the null hypothesis says that mu is less than or equal to some specified value of mu naught, versus the alternative, which says that mu is greater than that value. So we have a two-tailed test, a left-tailed test, and a right-tailed test. Notice that the direction of the inequality, at least in hypotheses that we're labeling B and C, the direction of the inequality is the same as the direction of the test. So in hypothesis test B, the inequality is pointing, in the alternative, is pointing to the left, right, less than, so that's a left-tailed test. And in the alternative hypothesis for hypothesis C, the inequality points to the right, and that's one way to remember the difference between a left and a right-tailed test. And then for hypothesis A, hypothesis test A, and the alternative, we're looking for values of mu that are either less than or greater than mu naught, so that's why it's a two-tailed test. So we've got these three types of hypothesis tests, and I'm going to label them A, B, and C, A for the two-tailed test, B for the left-tailed test, and C for the right-tailed test, so that we can link them up with the rejection regions and so forth in p-value formulas as we go on through the process. All right, now the next thing we need is the test statistic, and in particular the formula for the test statistic that we'll be using. And we're going to be using the standardized version of the test statistic. So instead of using just x bar, we're going to subtract from it the hypothesized value of the mean under the null hypothesis, and we'll divide that difference by the standard error of x bar, which is sigma over the square root of the sample size. So notice here that we are subtracting off the value mu naught, which was, and if I go back to the previous slide, it was the specified value, the hypothesized value in these hypothesis tests. So whatever that number is, that is what you would subtract off from x bar in calculating the test statistic. And to indicate or denote that what we're calculating is a test statistic, I'm going to subscript my z variable with the word calc. So z calc. So this is the calculation for the test statistic. Now, in order to use this test statistic in testing a hypothesis, we have to know how that test statistic behaves. And in particular, we need to know how it behaves under the null hypothesis and also under the alternative hypothesis. Now, that behavior is contained in its sampling distribution, so we need to know what the sampling distribution looks like under those two scenarios. So for this situation, if the null hypothesis is true, then the sampling distribution of z-calc is standard normal. In other words, z-calc has a normal distribution with a mean of 0 and a standard deviation of 1. On the other hand, if the alternative is true, and so depending upon which of the three hypothesis tests we're performing, it still has a normal distribution and it still has a standard deviation of 1, but if the alternative hypothesis is true, then the mean of that normal distribution, the mean of that sampling distribution, is something other than 0. Another way to think about these two statements is that if the null hypothesis is true, then the sampling distribution of z-calc will be centered at 0, and if the alternative hypothesis is true, then the sampling distribution of z-calc will be centered somewhere other than 0. Now, the rejection criteria for the test depend on whether we have a two-tailed test, a left-tailed test, or a right-tailed test. And so this is one of the reasons why we labeled those three hypothesis tests as A, B, and C. So if we're performing a two-tailed test, which was hypothesis test A, then we're going to reject the null hypothesis if the calculated value of our test statistic z-calc is either less than negative z sub alpha over 2 or if z-calc is greater than z sub alpha over 2. Now remember that z sub alpha over 2 is the upper alpha over 2 percentage point of a standard normal distribution. And let me also remind you that the alpha here is the significance level of the test. If we're performing a left-tailed test, that is hypothesis test B, then we're going to reject the null hypothesis for small values of our test statistic z-calc. And in particular, at a significance level of alpha, we're going to reject the null hypothesis if z-calc is strictly less than negative z sub alpha. And then finally, if we're performing a right-tailed test, that is hypothesis test C, then we're going to reject the null hypothesis for large values of our test statistic z-calc. In particular, if z-calc is greater than z sub alpha. So these are the components of the hypothesis test that we need to set up and utilize. If I scroll back a few slides here, we have our various hypotheses, our 3 hypothesis tests that we can perform. We have the formula for our test statistic, and we know something about the sampling distribution of the test statistic under the null hypothesis and also under the alternative hypothesis. And we use that information about the sampling distribution of the test statistic to set up our rejection criteria. So let's now look at an example. A company that packages salted peanuts in 8-ounce jars is interested in maintaining control on the amount of peanuts put into jars by one of its machines. Control is defined as averaging 8 ounces per jar and not consistently over or underfilling the jars. Now, we can imagine a production process. I guess we have an assembly line here, and we've got these 8-ounce jars going down the production line, and the machine is filling these jars with peanuts. And we would expect that from one jar to another, there's going to be variability in the weight of the peanuts dispensed. They're not all going to weigh exactly 8 ounces. So there is, in fact, variation from one jar to the next. And so in specifying what it means for the process to be in control, or the assembly line to be in control, we can't talk about it deterministically in the sense that every jar has 8 ounces or not, because that's not realistic. But what we can do is think about the population of jars being filled and say that, or define the process to be in control if the mean of that process, the mean of that population process is 8 ounces. And so that's how things are being defined here. Now, to monitor this control, what they're going to do is select a sample of 16 jars taken from the line at random time intervals and weigh the contents. And then the mean weight of peanuts in these 16 jars, so the sample mean weight of peanuts in those 16 jars will be used to test the hypothesis that the machine is indeed working properly. So we are going to draw an inference, draw a conclusion about the process, about the population of jars that are being filled, using the data that we have from this sample of 16 jars. If we conclude based on the data that the machine is not working properly, then we'll shut the process down, shut the assembly line down, and then make a costly adjustment. Now, suppose that the mean weight of peanuts in 16 randomly selected jars is 7.89 ounces. So, we've selected the sample, we've measured the weights of the 16 jars, and we don't have the raw data in front of us, but we're given the sample statistic of the sample mean being 7.89 ounces. Now, suppose also that it's known from past experience that the standard deviation of the weight of peanuts dispensed into jars by this machine is 0.2 ounces. So under that assumption, the question is, should the machine be shut down and adjusted? Well, to answer that, we're going to have to draw an inference or make a conclusion about the population based on the sample data. And so let's do this hypothesis test. So the first thing that I'm going to do up here at the very top is I'm going to define the notation that I'm going to be using in setting up my hypotheses. Now notice that in my hypotheses, the parameter that I'm using, I'm denoting by mu. All right, this is standard notation for the mean of a population. But what I want us to do is to define what that represents in a particular context. And so in this problem, mu represents the mean weight of peanuts being dispensed by the machine or by this process. So it's the population process mean weight of peanuts being dispensed. All right, and so with that in mind, the question is, how do we set up our hypotheses? Because we've got three potential sets of hypotheses that we can test. Well, we need to think about what it is we're trying to answer. And if I go back to the previous slide, if you look at this statement again, what we're looking to see is the machine underfilling on average? Is it overfilling on average? Or is the mean equal to 8 ounces? And so we're looking for a mean of the population being different than 8 ounces. And one of the ways of thinking about how to set up your hypotheses is that you put what you're trying to show in the alternative hypothesis. So this is how we're going to set up our hypotheses. We are going to assume that the process is in control. In other words, we're going to assume that the mean weight of peanuts being dispensed is in fact 8 ounces, and we're going to let the data try to convince us otherwise. So that is why we set these up this way. Notice that the two statements in the null and alternative hypotheses are opposing statements. They are logical complements. The opposite of mu being equal to 8 is mu being not equal to 8. All right, and so it's always going to be the case that the statements in the null and alternative hypotheses are logical complements. Now over here to the right, I'm just going to note, mainly as a reminder to myself, that I'm going to assume that the population standard deviation is 0.2 ounces, and this is based on previous experience with this machine, apparently. We'll talk more about this later, but for the purposes of the example and this particular section, we're going to assume that we know sigma. And I'm also going to just make this note over here that the sample size that we're using is 16. All right, now let's see here. Did it tell us which significance level to use? It did not. All right, so I'm just going to pick a commonly used significance level of 0.05. So alpha, remember, is called the significance level, and it's the probability of committing a type 1 error. It's the probability of rejecting the null hypothesis when in fact the null hypothesis is true. Now, what does a type 1 error represent in the context of this problem? What that represents is shutting down the machine unnecessarily. In other words, concluding that the mean weight of peanuts being dispensed is not 8 ounces when in fact it is. And if we conclude that mu is not equal to 8, remember what we said, we were going to shut down the machine and recalibrate it. And so a type 1 error would be rejecting the null hypothesis, concluding that mu is not equal to 8, and therefore shutting down the machine and recalibrating it when in fact we didn't need to because the mean was 8. Now we want that probability to be fairly small. We don't want to be shutting down the machine unnecessarily very often. And we could use any significance level we use. We could use 1%, 5%, 10%, but I'm going to use 5%, 0.05 for this example. And so what this means is, over time, if we consider all of the situations where the machine is in control, this is a quality control process, so this is going to be performed on a regular basis, perhaps daily, then in the long run, we're going to shut down unnecessarily only 5% of the time. That's what that alpha represents. Okay, then, when I write these out, what I like to do is write out the formula for my test statistic. And what I'm doing here is writing out the formula, and I'm not going to put in the sample value yet because I can set this whole thing up before I ever collect my data. So if we think about a quality control process, this process is well defined. There's a protocol for it. They've got it stored in a notebook somewhere. Every time they perform this process, they pull the notebook out. They run down the steps in this hypothesis test. And so here I'm writing out the formula for the test statistic. So zcalc is equal to x bar minus mu naught. Well, mu naught is 8, so I'm going to put that value there. Don't put mu naught here. Don't put the notation mu naught. Put the value like I have. We're assuming that sigma is equal to 0.2, so I'm going to put that there. And then we know that our sample size is 16 and the square root of that is 4. So I'm going to put that right there. Okay, so we've got the formula that we're going to use for calculating the test statistic once we have our sample data. Now we have to define the rejection region. Now because we have a two-tailed test, this is hypothesis test A, right? So we have a two-tailed test. So I'm going to reject for either small values of my test statistic or for large values. And because my significance level is 0.05, the critical point that I'm going to look up from the t-table is z sub 0.05 over 2, or z sub 0.025. We know that this z value is 1.96. And so the negative of that would be negative 1.96. And so the rejection criteria is to reject the null hypothesis if our test statistic z-calc is either less than negative 1.96 or greater than positive 1.96. So I've set up my test. And let me just point out that you can get all the way down here to this part, specifying the rejection region, without actually having conducted the experiment yet, without actually having collected the data. And this is a good practice to get into. You should always define the protocol or the process that you're going to use to make decisions in the context of your experimentation. And you should do this before you ever start your experiment, because this is going to inform you as to the type of data that you need to collect. And so it's always good to set up the process or protocol for analyzing your data before you actually conduct your experiment. But to get any further, we're going to actually have to collect the data by performing the experiment. And so that's been done. All right. The sample of size 16 was collected, and the sample mean was calculated, and that sample mean was found to be 7.89 ounces. And so now the question is that sample mean of 7.89 different enough from the hypothesized value, the desired value of 8 ounces for the population mean, to lead us to conclude that the machine is out of control? Well, it's hard to know that just by looking at this single number. What we have to do is we have to think about not only this number, not only this point estimate from you, but also the variability associated with the sampling distribution of X bar. And that variability is contained in its standard error. And so that's why we not only subtract the hypothesized value from X bar, but we divide that difference by the standard error of X bar. And so when we do that, we get a calculated test statistic, a z-calc value of negative 2.2. Now, what do we do with that? Well, we go back up and we look to see, has our rejection criteria been satisfied? Are either of these two statements true? And in fact, the first one is. And we would say since z-calc, since negative 2.2 is strictly less than negative 1.96, we reject the null hypothesis and conclude, therefore, that the alternative hypothesis is true, which says that mu is different than 8. In other words, we conclude that the average weight of peanuts being dispensed is not 8 ounces, and hence the machine should be shut down and adjusted. So again, we conclude that at the 0.05 level of significance, there is sufficient evidence that the average weight of peanuts being dispensed is not 8 ounces, and therefore the machine should be shut down and adjusted. So that's how we perform a hypothesis test about a population mean. We performed a two-tailed hypothesis test. We've used sample data to draw an inference or a conclusion about the population or the process based on that sample data. Now let's look at what's called the p-value. The p-value of a test is a measure of the consistency between the null hypothesis and the observed sample. In particular, the test statistic computed from that sample. Smaller p-values indicate greater inconsistency between the test statistic and the null hypothesis. If the inconsistency between the null hypothesis and the test statistic is great enough, in other words, if the p-value is small enough, then that will lead us to conclude that the null hypothesis is in fact false. Now, if you think back to when we first started talking about the principles of statistical inference, and in particular talking about the general ideas behind hypothesis testing, what we said was that in performing a hypothesis test, we set up our hypotheses. We have the null hypothesis and we have the alternative hypothesis. And at some point we collect data, and we compare the data that we've observed with the statement that we're making in the null hypothesis. And if the data are inconsistent enough with that null hypothesis, we're going to reject the null hypothesis and conclude that the alternative hypothesis is true. And so this p-value that we're talking about on this slide is a way of measuring whether or not the data are consistent or inconsistent with that null hypothesis. And so from that standpoint, it's a very natural thing to compute, okay? Because I think that how we've described this hypothesis testing process in general is a fairly intuitive approach. If we have an underlying assumption, an underlying belief about something, and we collect empirical data related to that something, if the data that we collect are inconsistent with that prior belief, then at some point we may want to conclude that that prior belief is not true. So this is a very natural decision-making process. Now, we do have to be careful and make sure that we interpret the p-value correctly. All right, it's for whatever reason very easy apparently to interpret the p-value incorrectly. On the next slide, this is where we actually define the p-value. And so the p-value associated with an hypothesis test is defined to be the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed in the sample, computed under the assumption that the null hypothesis is true. All right, so let me say that again. The p-value of a hypothesis test, it's a conditional probability. So this is one of the reasons we looked at probability so much. The p-value is the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed in the sample, and we compute that conditional probability under the conditions or under the assumption that the null hypothesis is true. Now, when we say at least as extreme, that is relative to the particular hypothesis that we're talking about, whether we're talking about a two-tailed test, a left-tailed test, or a right-tailed test. And that's what we mean here when we say as indicated by the alternative hypothesis. Okay, so that's how the technical definition of the p-value expressed in words, right? So it's very important that you understand this. So make sure that in your notes you really emphasize this and you commit this definition to memory. All right, now based on this definition, we can see that the p-value, it depends on the sample. It's a function of the sample because it depends on the observed data. And it also depends on the hypotheses being tested, whether it's a two-tailed test, a left-tailed test, or a right-tailed test. Now, how do we calculate p-values? We've got a verbal description on the previous slide, but how do we actually calculate the p-value for a hypothesis test? Well, it depends on the type of test we're performing, right? Whether it's a two-tailed test, a left-tailed test, or a right-tailed test. So again, we've got three formulas, and they're labeled A, B, and C that correspond to the three types of hypotheses that we've labeled A, B, and C. And so if the if we're performing a two-tailed test, hypothesis test A, then the p-value for that test is equal to 2 times the probability that the standard normal random variable z is greater than or equal to the absolute value of the observed value of z-calc. So again, z-calc is the calculated value of the test statistic. If we're performing a left-tailed test, hypothesis test B, then the p-value is equal to the probability that the standard normal random variable z is less than or equal to the observed value of z-calc. And then finally, if we're performing a right-tailed test, hypothesis test C, then the p-value is equal to the probability that the standard normal random variable is greater than or equal to z-calc. Now, one thing I want to point out, in the formula for the two-tailed test, the p-value for the two-tailed test in formula A here, notice that we're taking the absolute value of z-calc, but we're not taking the absolute value in the formulas for the p-value for the left-tailed test nor for the right-tailed test. It's only for that two-tailed test where we take the absolute value of zcalc. And again, as indicated down here in the text below, capital Z here represents the standard normal random variable, and zcalc is the calculated value of the test statistic for a given sample. Okay, so going back to the previous example, the previous hypothesis test, what is the p-value for that test? Well, the p-value is 2 times, this was a two-tailed test, so the p-value is 2 times the probability that the standard normal random variable z is greater than or equal to, and then I hope you can read my writing here. These are supposed to be vertical absolute value symbols, okay? So the absolute value of negative 2.2, which is positive 2.2, right? And so this is 2 times the probability that the standard normal random variable z is greater than or equal to 2.2. And you can look this up in the standard normal table, all right? This probability is 0.0139. And then we multiply that by 2. We get 0.0278, and so that is the p-value for this test. And then as we indicated when we talked about these things back in Module 3, we said back there that the way that we use the p-value is to reject the null hypothesis if the p-value is less than or equal to alpha. So here's the criterion that we're looking for. If the p-value is less than or equal to alpha, then we reject the null hypothesis. And since 0.0278 is less than or equal to 0.05, we would reject the null hypothesis and conclude that mu is not equal to 8. So let me just stop here and say, well, you're probably thinking, I thought we already came to that conclusion. Why are we looking at this? That's a great question. There are 2 ways to draw your conclusion. We can use the approach that we used when we looked at the example initially, where we compare the value of the test statistic to the critical points in the rejection region. Right? So we would call that the test statistic rejection region method. Or you can draw your conclusion using the p-value method, which is what I'm demonstrating here. So I'm just showing you another way to draw that conclusion. You don't have to do both in a given situation because you'll get the same answer. Right? These are completely equivalent approaches. In that sense, you'll draw the same conclusion whether you use the p-value method or the test statistic rejection region method. But we do need to know how to calculate p-values, how to interpret p-values, and how to use p-values in drawing conclusions in the context of a hypothesis test. And that's what we're looking at here. Now, let me show you graphically what a p-value represents, or what this p-value of 0.0278 represents in this context. And so this is just a very roughly sketched graph. And so if the null hypothesis is true, then the sampling distribution of the test statistic zcalc is a standard normal distribution. And so this is my attempt at drawing a standard normal curve. So it's this bell-shaped curve, it's centered at 0, and it has a standard deviation of 1. Okay, so if the null hypothesis is true, then zcalc has this distribution. All right, and there's a very high probability that zcalc is going to be somewhere close to 0. In this particular situation, the observed value of the test statistic was negative 2.2, correct? And so because we have a two-tailed test, because we're looking for values of the test statistic that are either a lot different from 0 in the negative direction or a lot different from 0 in the positive direction, what we're going to do is take this distance, the distance being 2.2, and we're going to mark off that distance on the left side and also on the right side. And what we're going to do is look at the probability, calculate the probability of observing a value of zcalc either at or to the left of negative 2.2, so somewhere out here, or out in this tail. And we're going to compute that probability under the assumption that the null hypothesis is true. So again, if the null hypothesis is true, the distribution of zcalc is this normal curve centered at 0 with a standard deviation of 1. And so if the null hypothesis is true, the probability of observing a value of z-calc at least as extreme as that which has been observed. In other words, either at or to the left of negative 2.2 or at or to the right of positive 2.2, that probability is 0.0139 plus 0.0139, which is 0.0278. So do you see that? If the null hypothesis is true, the probability of observing a value of z-calc out here in this left tail, at or to the left of negative 2.2, is equal to the area under the standard normal curve above that interval, which is 0.0139. And if the null hypothesis is true, then the probability of observing a value of z-calc at or to the right of positive 2.2 is, again, this area under the curve over that interval, which is 0.0139. And so that combined probability, this is why we take twice the probability, all right, because we have to consider both tails in this two-sided test, this two-tailed test. So that is what the p-value represents, all right? It's equal to 0.0278, and it's equal to observing a value of z-calc either out here or out here, if in fact the null hypothesis is true. Okay, so that wraps up this example for now. We may revisit it a little later, but I think this is probably a good time to stop, and so we'll pick up the material in the next video.